Greetings, I'm John the Spirit.
I'm Arch Ezekiel.
We have titanium because we're strong, and welcome to Greg Supershorts. In the previous episode, I teased you about our titanium system. So let's talk about it now. Here we have bauxite ore that's being forge hammered and ore washed into purified bauxite ore. Thermal centrifuging it requires some extra rutile, which is part of the process for titanium, and then we take the thermal centrifuged purified bauxite ore and forge hammer it to get bauxite dust, which we can then electrolyze to get more rutile. As a result, we also get aluminum dust, obviating our system here that made aluminum dust from nether aluminum ore, but whatever. Once you have rutile dust, you can combine it with carbon and chlorine to get titanium tetrachloride, a liquid. In an electric blast furnace, each bucket of titanium tetrachloride, combined with 2 magnesium, makes hot titanium ingots and magnesium chloride dust. The magnesium chloride dust can then be electrolyzed into chlorine dust and magnesium dust, restoring all the original chlorine, I believe. To deal with that magnesium chloride, we have an ME precise export bus, which exports magnesium chloride at a precise rate of 3 into this advanced electrolyzer. So that's our first step into EV, titanium. The next is to use phosphorus-doped monocrystalline silicon boules. Phosphorus-doped wafers with a glass lens yellow can be turned into SoC wafers, which turn into system-on-chips, which make LV and basic MV circuits easier. Suddenly, you don't need any SMD components. And you get your circuits at a higher rate. To get the boules, you need silicon, gallium arsenide, nitrogen gas, and this phosphorus dust. We chose to make 8 of these at once because they take 10 minutes, so we needed 64 phosphorus dust. We chose to make that from 5 stacks of phosphate dust, which we got from 10 stacks of monazite dust, which we macerated from monazite, which you can get from smelting N monazite ore at a good rate. With our HV macerator, this process was nice and fast. One warning is that if you just stick silicon dust into your system with a programmed circuit of 2, even if you have the ingredients for the better boules, it'll try and make the shitty boules instead. The recipe for the phosphorus boules requires no programmed circuit, while the recipe for the silicon boules requires a programmed circuit of 2. Thankfully, we have so much silicon, this was not a problem. You need to cut them in an HV cutter in a clean room, which is why our clean room is now full of stuff. Thankfully, we just crafted about 69 plascrete so that we can expand the clean room. 69 was insufficient. Turns out we needed like 500. We're making a very large clean room, so we never have to expand this thing again. It's 12 by 12 by 7, and we'll have a cute little doorway running through the center. The main cost was these 91 filter casings, which I will now make. To make those SoC wafers, we need a yellow glass lens, which we can get from a glass lens and yellow dye. Yellow dye is pointlessly annoying, requiring sulfuric acid, salt, and a yellow dye, which we'll get from the market. 1 single dandelion will be enough. We can get the glass lens from a glass pane in a lathe, which we can get from glass in a cutter. With the yellow lens and the advanced laser engraver, we are now ready to be able to automate circuits. Alright, we've now put the patterns in the pattern provider. We don't need to make them right now because we have enough circuits of both types. Just kidding. We need a ton of EV circuits. Because our next step into EV is to make the large combustion engine, which can make 6144 EU per tick at 1.5 times fuel efficiency, i.e. 3 amps of EV power. The only issue is that it requires an EV dynamo hatch to output its energy. That requires an EV assembler. The NPIC chip requires an EV cutter. The extreme voltage coil also requires an EV assembler. And if you want the tungsten steel, that's a whole nother set of EV items. We already have the EV blast furnace that lets us turn tungsten steel dust into hot tungsten steel ingots, but for some reason tungsten steel requires an EV mixer because mixing things like tungsten steel is really hard. I'm not salty at all. The tungsten dust requires an EV electrolyzer, and the tungstic acid dust to get that requires an EV chemical bath. So we've got like 5 EV machines to make. Because I just want to make 64 EV circuits, I'm going to set up the recipes required for that now. And now I'm going to make 60 EV circuits. It's just gonna happen. This is madness. Our HV machines in the clean room were, for some reason, not all working at the same time. They had insufficient energy inputs. Turns out that's because the HV diode requires a soft mallet to change the amperage throughput. So we're increasing it to 16, because of course we are. Because I think it's funny, I feel I should tell you about this vacuum freezer that we've had for like several dozen hours. At some point we just made this and forgot to tell you about it. It just requires some EV circuits and frost-proof aluminum machine casings, which require aluminum, and the only thing it does is cool down hot ingots. So we just have export buses on this vacuum freezer that export all of the types of hot ingots, and then they get automatically imported into the system. That is why all of our crafting recipes say that they create the actual metal and not the hot metal, because AE2 recognizes the metal once it pops into the system. So if we just let a hot metal pop into the system, and then turn the hot metal into the cold metal, and let that pop into the system, then AE2 would be like, wow, you did it! It just works. The intense strain we put in our auto-crafting system by trying to make 60 EV circuits is a problem when you're trying to do other things at the same time, and all of your wire mills and lathes are being used, and your only option is to stick aluminum in a basic wire mill like a fucking chump. As it turns out, the MV circuit recipe that we tried to use using system and chips requires an IV circuit assembler, so oh well. Alright, we can make MV circuits again. The one problem is that we didn't make a laser engraver for CPU wafers, which are needed for the current MV recipe, so I think eventually we'll fix that. It's really unfortunate. Anyway, now that we have all these EV machines, we can start automating them. We've put them in the clean room because the cutter specifically needs to be in the clean room. Behind the mixer, we do have an EV to HV 4-amp transformer, so that we can run them. Tungstic acid is now automated in the chemical bath. We've chosen the Scheelite recipe, because, I don't know, calcium chloride seems cool, I guess. We can use it to make nether star dust eventually. And we don't currently have a source of calcium, so we'll make sure to automatically export 3 calcium chloride dust into our auto-processing electrolyzer. The one other thing is, you need helium to run things like hot tungsten steel ingots faster. While we can't currently make our parallel EBF EV, there are some recipes at HV that we could run using helium in this system, and we would like to. Anyway, as another step in our process to make the EV combustion engines, we decided to set up an array of 6 extruders. So we could finally automate small and large gears and rotors and rings, and it's all wonderful. Thanks to the power of these extruding machines, I now have the many items required to make our large combustion engines. We're putting 3 of them underneath the EBF setup, which, by the way, Arch is about to fix with a new method. I'll talk to you about it once we have it. As it turns out, these large combustion engines can share at least one wall. If we weren't trying to feed it oxygen to make more EU, we could share even more walls of these large combustion engines, but unfortunately, to fit 3 fluid hatches for the oxygen, lubricant, and diesel, we can only share 1 wall. So I can only have these here in increments of 2. However, I need 3 of these EV combustion generators to run all of the blast furnaces. Unless I use these extra 8 HV combustion generators to produce the 2 EV amps that these 2 combustion generators don't produce. These produce 6. So that's what I'm gonna do. I scammed us, unfortunately. I forgot that you need an IV dynamo hatch to enable oxygen boosting, and guess what hatch we do not fucking have. So we can run a grand total of 4 EBFs, which is the same speed as running 8 EBFs, except we're using double the power. I was so excited to have 1.5 times power efficiency, everybody, but no. We have to continue to progress. While Arch works on epoxy, which I'll explain later, I'm going to focus on making the EV circuit assembler. The hard part about the EV circuit assembler is the EV emitter, which requires radon. While making a steady supply of radon from ender air in a distillation tower is eventually a good idea, it's kind of expensive on power. It's easier for me to make a few buckets of radon gas in bulk. We can smelt plutonium ingots, so this part isn't an issue. We just need this uranium dust, which we can electrolyze from depleted uranium hexafluoride, which comes from uranium hexafluoride, which comes from uraninite, fluorine, and hydrofluoric acid in a chemical reactor. The many ingredients for the large chemical reactor unfortunately require program circuit 6, so I'm setting up an HV assembler specifically for that purpose. We've also set up an EV chemical reactor for crafting, and we're going to set up an EV large chemical reactor back here for manual stuff. Okay, I've just made 10 buckets of uranium hexafluoride, so I can now centrifuge it. You need an HV centrifuge to perform this recipe. When this is done, we'll have 9 worth of uranium-238. Alright, we are now getting quantum eyes, 4 of them. Alright, we are now proud havers of an EV circuit assembler. The main other ingredient we need for the nanoprocessor is all this epoxy stuff. We're making most of it in an EV chemical reactor on Autocraft, as opposed to making an actual system for it, because we think it doesn't really matter that much. Sodium hydroxide can be obtained by making salt water, which we are just mixing water and salt for. Bisphenol A is made from phenol, acetone, and hydrochloric acid. You've already seen that we have hydrochloric acid and acetone being made, but to make phenol, we have an HV distillery constantly turning heavy fuel into phenol. We're just taking the heavy fuel from the system that makes toluene because it makes more than enough heavy fuel, more than fast enough. Finally, to make the epichlorohydrin, instead of using allyl chloride, which requires propene, which who knows how we're going to get that, we are using glycerol. You can get glycerol from a variety of methods, but seed oil and methanol is the one we chose. Where are we getting all of our seed oil? We have here 3 random seed generators constantly shoving seeds into these basic extractors to make lots of seed oil. Once you have epoxy, you can solidify it in a plate to make epoxy sheets. Then we use a chemical reactor with sulfuric acid and gold foil to get the circuit boards, and another chemical reactor with iron 3 chloride and electrum foils to get the printed circuit boards. At this point, we're almost done with the HV nanoprocessors. Next up is the nano CPU chip. The nano CPU wafer is not another laser engravered wafer. It requires liquid glowstone, CPU wafers, and raw carbon fibers. To make raw carbon fibers, you need to combine carbon dust with any of these interesting fluids. The least efficient recipe and the most tempting is to use polyethylene, but as it turns out, the liquid epoxy to nano CPU chip ratio is 2.5 millibuckets of epoxy per nano CPU chip. And so since an epoxy printed circuit board is 144, this is basically 146 epoxy. So it's a negligible amount. Nothing weird is required to turn these HV circuits into EV circuits. The IV circuits, however, unfortunately require NOR memory chips, which are made from NOR memory wafers, which are made from a pink glass lens, so we need another laser engraver, which is the only annoying part. I mean, it's fine otherwise, it's just stuff we have. Okay, so now that we have our NOR memory wafers, it's time for step 1. Replace our HV pattern with the cool new super improved nanoprocessor recipe. And now for the cool new super improved EV circuit recipe. And now for the cool, new, super improved IV circuit recipe, which requires NOR memory chips. And now for the cool, new, extra super, well, not improved, it's our first LUV circuit recipe. With that firm step into the IV age, let's stop with progression for this episode and finish with one last thing. This system for the blast furnaces. We are no longer using nodes to run these blast furnaces in parallel. Instead, we're using the power of AE2 to round-robin recipes to different sides of the pattern provider. We have 4 subnets set up on this pattern provider, connected to interfaces. Each subnet goes to a fluid input hatch and a chest. Both subnets on this side of the blast furnace go into the same chest, since the input bus underneath it is shared by the 2 sides. Since each fluid input hatch connects to 2 EBFs, all our recipes have a size of 2 ingots. That way, whenever the system round-robins to a different subnet, it shoves enough items for both blast furnaces connected to each fluid input hatch to run. If all 8 EBFs were working, God, please, we would be able to run even faster. However, getting the IV dynamo hatches to upgrade our EV combustion engines is quite the doozy. So we're going to need another episode for that. For now, that's it for today's one. As always, if you have any feedback, we'd love to hear it. We hope you enjoyed!